Example 5.5. A hollow sphere has potential at its surface given by V of theta, phi. Find the potential inside the sphere. Solution. For the potential inside the sphere we have, see the following equations, where cosine gamma equals cosine theta, the cosine of theta prime plus sine theta, the sine of theta prime, the cosine of phi minus phi prime. Using a relation on Legendre polynomials like before, see the equation. Note,
see the following equations. So,
see the following equations. Equals a squared minus or squared over 4 pi the integral of d omega prime v of theta prime phi prime times r squared plus a squared minus 2a r cos gamma raised to the exponent negative 3 halves end exponent. So we have a second way to express the potential. See the equation shown. Example 5.6. 2-point charges, plus or minus q, are placed at positions plus or minus a on the z-axis. Find the potential as an expansion in spherical harmonics. B. Keep qa equals p divided by 2, a finite constant, as a goes to 0, and find the potential for everywhere except r equals 0. This is a dipole at the origin directed along the z-axis. C. Consider the dipole in part B with a surrounding grounded spherical shell at radius b. Find the potential inside by linear superposition.
Solution. A. The potential of the two charges is r is greater than a. See the following equations. The potential for r less than a then is of the form regular at the origin, with matching coefficients with the above, such that we simply have. See the equation. B. Let's take a goes to 0 while keeping qa equals p divided by 2 constant in the above form valid for r is greater than a. See the equation shown. Thus, in the limit of the definition for a dipole, we find the dipole potential to be.
See the equation. C. Inside a grounded shell radius b we get the added charge induced on the shell such that it is at 0 potential. Let's describe the potential inside the sphere for the induced shell charge alone, i.e., with the previous inner form but new coefficients to be determined. See the equation shown. At r equals b the grounded shell must have a superposition of contributions such that the shell has 0 potential at all orders of r, i.e. we must have agreement on coefficients such that. See the equation. Thus, see the equation shown.
And for r is less than a we get. See the equation. Example 5.7. Consider 3 charges on the z-axis. A-2q charge at the origin and 2q charges at plus or minus a have this be inside a grounded conducting sphere of radius b greater than a. First consider the description for the potential when there is no grounded sphere and show the limiting form as a goes to 0 while keeping qa squared equals q. Use spherical coordinates. B. Repeat for description of potential inside the sphere when it is added, for r is greater than a, and r is less than a cases, and as a goes to 0 while keeping s squared equals q. Solution. A. The potential is. See the equation shown. Shifting to spherical coordinates we have
1 over the absolute value of our vector minus az equals the sum from L equals 0 to infinity of r sub is less than to the LTH power over r sub is greater than raised to the L plus 1 power p sub L of cos gamma, gamma equals theta, and 1 over the absolute value of our vector plus z equals the sum from L equals 0 to infinity of r sub is less than to the LTH power over r sub is greater than raised to the L plus 1 power p sub L of cos gamma prime equals pi minus theta. Since gamma prime equals pi minus gamma, we have p sub L, the cosine of gamma prime, equals -1 to the LTH power times p sub L of cos theta, allowing grouping to get. See the equation.
First consider r sub is less than equals a. See the equation shown. Now let a goes to 0 while qa squared equals question. See the equation. B. The potential due to the charge induced on the sphere alone has the form See the equation shown. For A is less than R is less than B, we then have by superposition. See the equation.
Notice that the L equals 0 terms are cancelled in the first sum. Let's take R goes to B, where the potential should be 0 at the grounded sphere. Phi sub tot of R equals B equals 0. In other words, see the equation shown. Examining by order. A sub 0 equals 0 and a sub ODD equals 0, while for the others, see the equation. Thus, we have for the potential, see the equation shown, and see the equation.
Notice in the latter, the L equals 0 terms don't cancel like before. Returning to the A is less than R is less than B form for evaluation in limit A goes to 0 while QA squared equals Q we get. See the equation shown. Example 5.8. Consider a cylinder, radius B, with axis on the z-axis, with bottom at z equals 0 and top at z equals L. Suppose the potential on the ends is 0 while on the sides it has potential V of phi, z. Solution. As before, we have phi equals R of rho Q of phi z of z with. See the equation. An m integer value for Q to be single valued. Similarly, we have.
See the equation shown. And the boundary conditions z of 0 equals z of L goes to z equals the sine of n pi z over L. We thus get the radial differential equation in the form of the modified Bessel equation. See the equation. The solutions consist of the modified Bessel functions. I sub m of k of rho, k sub m of k of rho. Since rho equals 0 is in the region of interest, we only need I sub m of k rho. See the equation shown. To find A sub mn, B sub mn, expand V of phi, z equals phi of B, phi, z in a Fourier-Bessel series.
See the following equations. Thus, see the equation. We thus have. See the equation shown. With special cases.
See the equation. And B sub 0, n equals 0.